In this video, we're going to be looking at 3 more optimization problems. And what I encourage you to do, same as last time, is at the beginning of each problem, pause the video and see how much of it you can do on your own. And then unpause and see how well you did. Okay, so a closed box has fixed area A and a square base with side X. So it says find a formula for its volume V as a function of X. We know that the box has a base that's square, so side X and X, and it has some unknown height, this box does. And the box is closed, so this must be X and X and X and X. And these heights we don't know, so let's just call them H. So those are all H. So it has a fixed surface area. So the surface area, there's 6 faces. All of these faces here are going to be, there's 4 faces that have area hx plus 2 faces that have area x squared. We want to find a formula for its volume as a function of x. Well, we know that volume is going to be x squared h, so we need to get h in terms of x. So let's go to this surface area equation that we developed. And this is fixed. This is a constant, so we can treat it as 1. So we know that s minus 2x squared equals 4hx. So h equals s minus 2x squared over 4x. So we can replace this into here. We get the volume equals x squared times s minus 2x squared over 4x. And if we simplify that a little bit, we're going to get, let's see, sx minus 2x cubed over 4. Then it says sketch a graph of v against x. Well, since we don't know the surface area, it's going to be hard to get a good sketch of that. But let's just think about what type of graph that we're looking at. This is going to be a cubic. It's a cubic where its leading coefficient is negative. So we're going to get something that looks like that. And we want to find the maximum value of v. So to find the maximum value of v, v max is going to occur when my derivative equals 0. So to find my derivative function, we can pull out that divided by 4 is just 1/4. And then if we take the derivative of this top, we're going to get s minus 6x squared. Where does that equal 0? Well, that's going to equal 0 when s minus 6x squared equals 0. And solving this, we get s equals 6x squared, or x equals plus or minus the square root of s over 6. And since we're talking about positive values, or since we're talking about dimensions, it can't be negative, so it's just positive s over 6. And is this a maximum or a minimum? Well, we know that drawing our derivative chart, so we have x and s prime, and we've got x less than root s minus 6, x greater than root s minus 6. It's going to be 0 there. Well, when x is less than that, we're going to get a positive value inside. And when s is greater, or sorry, when x is greater than square root of s over 6, and I plug that into there, this whole thing is going to become negative. So that implies we go positive, 0, negative. We've got some sort of max. So therefore, it's clear that it's a max. And so what is the maximum volume? Well, the maximum volume is going to be x squared times my height. Where my height is s minus 2x squared over 4x. And then I need to plug in the x that I found. So plugging in the x that I found, let's actually do this on another page. So I found out that it's going to be maximized at this for this value of x. V is a maximum when x equals square root of s over 6, and then we can just plug that into my volume equation. So the actual volume that I'm going to have is x squared, which is going to be s over 6, times s minus 2 times x squared, which is s over 6, all over 4 times x. And we could simplify that a little bit. My volume is s over 6 times s, just making it clear that it's in fact an s and not a 5, minus s over 3 all over 4 s over 6. And we could simplify this a little bit further, but for the case of this problem, I think this is good enough. This gives us an understanding of the volume in terms of s. Just to, I guess, just to be a little bit more, have it be a little bit more satisfying, we could say that the volume equals s over 6 times 2/3 s over 4 s over 6, which is well, let's see, 12, so s squared over 36 times s over 6. And of course, you could rationalize it, but let's just stop. So the idea being, we found an expression for the volume. Let's go back. We found an expression for the volume. We express h in terms of x. Given my fixed surface area, we found the derivative. We set the derivative equal to 0. Found a value of x for when the derivative equals 0, and then plugged that value of x back into the volume of equation. And when we plug that value of x into our volume equation, and then we simplified, we get down to something like that. All right, another problem. The cross section of a tunnel is a rectangle of height h and surmounted by a semicircular roof of radius r. If the cross-sectional area area is A, so it's a fixed cross-sectional area, meaning that this area is fixed, determine the dimensions of the cross-section which minimize the perimeter. Okay, well, let's get an expression for the perimeter. The perimeter is going to be 2h for that, plus 2r for this. That's r, this is r, that's 2r. And then the perimeter of half a circle, well, we know that the perimeter of a circle is 2 pi r. So the perimeter for half a circle is just going to be pi r. So this distance here is pi r. Okay, so we right now have two variables here. We've got h and r. So if we're trying to minimize the perimeter, we need to get this perimeter equation in terms of one variable. Well, what we know, we also know that the area, which is fixed, so this is a constant, equals half the area of the circle. So, pi r squared over 2 gives me this area, plus 2rh gives me that area. What is the easiest thing to solve for here? I think clearly it's h. So we can find that h equals a minus pi r squared over 2 all over 2r. But this comes from solving this equation here for h. So I just subtracted this and then divided by 2r. Simplifying this a little bit, we get h equals a over 2r minus pi r squared over 4r. And now let's actually go ahead and do the work. Now that I know I have h as a function of r, I can plug this in for h and take some derivatives. So let's do that, and let's do that on this next page so I have some room. So my perimeter equation is going to become, let's see, p equals 2 times h, but h equals a over 2r minus pi r over 4, getting rid of the unnecessary r, plus 2r plus pi r. And if we simplify that even further, we get that this equals a over r minus pi r over 2 plus 2r plus pi r. And we want to, this is my perimeter, we want this to be a minimum. So this is going to be a minimum when my derivative equals 0. So we find p prime. So p prime, we're taking the derivative with respect to r. Just as a reminder, a over r we could write as a times r to the negative 1. So the derivative of this becomes negative a times r to the negative 2. Keeping in mind that a is just a constant, so we just keep it in front. It's not affecting my derivative. So we have, that's the derivative of that, minus pi over 2 plus 2 plus pi. This is just r, r, r. So those are linear functions, so the derivative becomes just a constant. Okay, so now I want to set this equal to 0, so I get 0 equals negative a times r to the negative 2 minus pi over 2 plus pi. I could simplify that to just plus pi over 2 plus 2, combining these two. Okay, well, doing a little bit of solving, we get a times r to the negative 2 equals pi over 2 plus 2. Rewriting this so that it makes a little bit more sense to us. A over r to the 2. Doing some cross multiplying, we get r squared equals a over pi over 2 plus 2. So therefore, my r, my radius, must be the square root, and not the minus square root, because remember, we're talking about actual real dimensions. So the square root of a over pi over 2 plus 2. And that's the radius of the semicircle that will minimize the perimeter. But the question says, determine the dimensions of the cross section. So to be fully to answer this fully completely, the dimensions need to include the height. So this is my radius, and my height would be plugging that radius in for here. So the height is going to be area minus pi times radius squared, which is just a over pi over 2 plus 2 divided by 2 all over 2r. So all over 2 times the square root of a divided by pi over 2 plus 2. So again, messy. We could further simplify it, but that's the key work that we wanted to do. What we did, just to kind of re-talk through this problem, it was a fixed area, so we got an expression for the area. It was a changing perimeter, so we got an equation for the perimeter. We wanted to make this perimeter a minimum, and we'd want to do that so that we were using the least amount of materials possible. So what we needed to do is we needed to get h in terms of r, so we did that by solving my area equation for h, and then I plugged that h in for here, which gave me an expression for the perimeter that was all in terms of r. Well, what I did is I found its derivative, I set it equal to 0, and I solved for r. And that gave me the r value, the radius that minimizes the perimeter. And then I plugged that r value into my height equation to get the height. And that's the radius and the height, which will give me the minimum dimensions, or the dimensions that minimize the perimeter. All right, last question here. It says, what value of a makes, well, the following true? So first it says that makes the function have a local minimum at x equals 2. So for it to have a local minimum at x equals 2, that means that the derivative at 2 would be 0, and for less than 2, it's going to be negative, and for x greater than 2, it's going to be positive, so that we get a shape that looks like that. Okay, so let's take the derivative. The derivative equals 2x. Well, let's first write it as x squared plus a times x to the negative 1. So the derivative becomes 2x minus a x to the negative 2. And we want to set this equal to 0. And well, let's first solve this in terms of a. So we get a over x squared equals 2x, a equals 2x cubed, and we want to find, we want our derivative to be 0 when x equals 2. So we put 2 in for x, we get a equals 2 times 2 cubed, which equals 16. Let's just show that this actually works. What it's saying is that if I have some function x squared plus, well, 16 divided by x, we should have a minimum at x equals 2. Can't totally see it. Looked in the wrong direction. So let's go 10 and 50. So here's my function. Let's confirm that it's actually a minimum at 2. So 3 minimum. And confirmed. It's a minimum when x equals 2. So the reason why it had to be a minimum at x equals 2 is what I found the derivative of my function. I set it equal to 0, solved it for a to find that when for what values of a my derivative equals 0, and then we're forcing x to be 2. So we plug 2 in for x, and that says that if a is 16, then when x equals 2, there will be a minimum. What about for a point of inflection? So we'll do that on the next page. If we want to have a point of inflection at x equals 1, point of inflection is when the second derivative equals 0. So we know that the first derivative equals 2x minus ax to the negative 2. And again, we found that right here. So the second derivative is going to be 2 plus 2ax to the negative 3. And we want that to be 0. When x equals 1. So let's directly substitute x equals 1 in for here, and we get 0 equals 2 plus 2 a1 to the negative 3. So solving this, we know that this is just 1. So we get negative 2a equals 2. So a, therefore, is negative 1. And let's confirm again that this is true, just to be most prudent in our work. So if we go and switch that a value instead of 16 to negative 1, and graph it, we're saying we have a point of inflection at x equals 1, and it's pretty clear we're concave down until x equals 1, and then from there on we're concave up. If you want, well, if you want further proof, we could do math and derive and my derivative, if it's a point of inflection, should have a max at that point. So let's confirm. Well, actually, it should have a minimum at that point. So my derivative has a min at that point. Let's just be very careful that we're totally right. And this shows that when x equals 1, my derivative has a minimum, and if my derivative has a minimum, then my function has a point of inflection. Okay, so that's it for this. The optimization problems, you really just need to get familiar with all the different types of problems, just practicing doing them. The calculus is just taking the derivative, setting the derivative equal to 0, because that's where there's going to be a max or a min. The hard part about optimization problems is that oftentimes, the algebra is tricky, but more difficult is setting up what is the math that you actually need to be doing.